Hello, once again, I welcome you to another session of our power electronics lecture. And this time around, we want to look at power MOSFET, which is one of the PN junction devices for power electronics applications. So we want to quickly introduce ourselves to this device, and then we can look at other things, especially the construction and then operation, as well as the switching characteristics. Okay, we'll also look at issues that bother on its applications. Okay, all right. So introduction. MOSFET, okay, stands for metal oxide semiconductor field effects transistor, okay, and is widely used for high switching speed operation. Okay, so basically that is the meaning of MOSFET. Okay, now as a solid state device, so you will see MOSFET as one of the solid state devices for switching applications. Okay, it has comparatively high efficiency than when you take, for instance, a BJT. Okay, so MOSFET is far efficient than BJT in terms of its switching and so on. It can be classified into two, depletion mode and then enhanced mode. Okay, MOSFETs. Okay, so the figure here, or whether it's a figure or a tree diagram, is just helping us to put this MOSFET into classes. Okay, so you have the depletion mode MOSFET and then the enhancement mode MOSFET. So under each of them we have N and N P channel. Okay, so you have N channel D MOSFET and then the P channel D MOSFET. Okay, so for the enhancement also we have P channel and then N channel. Okay, like you can see. So we can now look at the construction of it, which is very important. So figure 9 here, which is a depletion mode N-channel MOSFET. Okay, will help us appreciate the construction. Okay, so a depletion type N-channel MOSFET, as we have in the figure, has a lightly doped P type substrate. So this is our substrate. Okay, that's our substrate, and it's a lightly doped P type, semiconductor material, if you like. So into which two highly doped N region, okay, that is N plus. N plus here means that we have doped it highly. Okay, so this doped material are actually diffused into it. Okay, so you use a diffusion process, diffusion into the substrate. Okay, like we have here. So the two N regions act as drain and then source. So you can see this N region and then another N region. Okay, so we treat them as drain and then source. Okay, going forward we will understand what all these things are. Okay, an N channel is also diffused between the drain, okay, and then the source. Okay, so like you can see, so that's an N channel. All right, so a thin insulating silicon dioxide layer, that's a SiO2 for silicon dioxide, okay, is grown across the entire semiconductor surface. So you can see this is the oxide layer. Okay, also over here. Good. So two holes cut into the oxide layer, allow contact with the source and then the drain, and a metal layer is then deposited on the oxide layer to form the gate. Okay, so you can see the gate here. So we're just describing the construction of it. So you have a metal layer here, deposit on the oxide layer, and then we can have the gate terminal here. Okay, all right. Now, due to this presence of oxide layer, okay, the silicon dioxide layer, the gate is insulated from the semiconductor. So you can see it's obvious that this is the silicon dioxide layer. So you put this layer on the N channel, okay, which you diffuse into the substrate, and then you put the metal plate, okay, on the layer. So obviously the layer now serves as an insulation between these two, that's the substrate with the end diffused into it and then the gate. Okay, so that is what is happening. Now the oxide layer makes MOSFET a high input impedance device. Okay, so because of this, it makes the input impedance for the device a very high one. Okay, that's because it serves as an insulation, more or less a dielectric. Okay, so the resistance there in terms of the for you to put potential on the gate, you expect easy flow or conductivity, it becomes a very difficult one because of this insulation. So it makes it a high input impedance device. So p-channel depletion type MOSFET, okay, consists of n-type substrates into which two highly doped p regions and p-channel are diffused. So we're just describing the converse of, if you like, what we are basically looking at. Okay, so if it is a p channel, all right, then it simply means that our substrate here, okay, is an n type. Okay, but because this one is n channel, our substrate here is a p type. Okay, so a p substrate. So this description on this point is just giving you the opposite, not the opposite, but to say that a p channel, okay, if one is n channel, the other is p channel. Okay, so that is what we are looking at as far as this session is concerned. Okay, so same concept. Take n substrates, then dope a p-type material into the substrates, diffuse a p channel, okay, and you have formed a p channel device, which is a MOSFET. Okay, so the two p regions act as drain and then source. Okay, so if you take, you can just basically look at it as far as this whole thing is concerned. So if this is a p channel, this substrate now becomes n substrates. Then this channel now becomes, okay, this channel, this is a channel. So that becomes a p channel. Then our source is as a result of high doping of p-type, okay, material. The same applies to the drain for a typical p-channel MOSFET. Okay, so that is what it is. So let's look at the gate operations. Okay, so take the positive gate operation. Let's make reference to this figure 9.1. So when the gate bias is positive, okay, the gate and the channel can be thought of as a capacitor. Okay, so like you can see over here, we want to put a positive gate or positive potential on the gate. So this figure, I am sure you can easily tell what type of channel we are dealing with. Okay, so this is an N channel, because our substrate is P, so N channel. Our gate is here, so we are biasing. What do we do? If you observe this thing carefully, you realize that the gate, okay, is one terminal or one contact point, source another terminal, drain another terminal. Then you also have the substrate, okay, the substrate. So we have a metal substrate. Okay, so you place the substrate on this metal, so that is also another contact point. Okay, but if you observe carefully, the source, see this connection, okay, the source and then the substrates are at the same potential. Okay, at the same potential. All right, so we can now say that we'll put a potential across the gate and then the source. For that matter, the gate and then the substrate, we can bias it. Okay, so it's the same. So they're saying that the positive charges, okay, on the gates induces negative charges in the N channel, as we have in the figure. Okay, so that the negative charges add to those already present in the channel. Okay, all right. So by just doing this connection with the presence of the oxide layer, what it is we have established is a capacitor. What did you put on the gate? It's a positive potential, so that because of that, on the gate contact, it will have positive charges collected at that, and then you also have oxide layer which separates the gate and then the substrate in which we diffuse the channel. So the other side, because the channel has N material diffused into it, you will have separation of charge, which is electrons or N materials. That is seen as a capacitor. Capacitor is nothing but what? Two parallel plates separated by, if you like, a dielectric or an insulator. Okay, so that is what is happening here. So the positive gate charges on the gate induces negative charges in the N channel. Okay, so that negative charges add to those already present in the channel. So we put positive here. Okay, what is happening is that any positive close to this area, because this thing is a p-type, all right, lightly doped p-type, so it has positive in it, the substrate. So any positive that is close to this place, we already know that light charges, they will repel. So the positive potential will push away anything that is positive, all right, from this region, and then seek to attract anything that is negative, because unlike charges will attract. So will attract, all right. That is why we are saying it will induce. What is that word? That's it. Okay, so maybe I can just go to my pointer option and then I can underline the word induce, okay, or induces. So that is happening over there. So by so doing, all positive charges in the substrate or close to the channel, the silicon dioxide will be repelled and the negative will be attracted. So it will add up to what is already diffused here. It will strengthen it. Okay, that's what I'm saying. Now, that's okay. So the positive gate voltage therefore increases or enhances the conductivity of the channel. Okay, so for positive gate operation, it will enhance the conductivity of the channel. Why? It's pushing away those positive, bringing negative. The channel is already induced, diffused with air, electrons, so it will promote it. Okay, so that's more positive the gate voltage, the greater the conduction from what? Source to drain. You understand? So if you make the gate voltage more positive, we are promoting conduction, pushing away anything plus here, and then bringing more electrons to add up to this diffuse one. And there's going to be flow of current from source to drain. That's the conduction we are talking about. So it will open up a link, and that link will enhance movement of electrons from source to drain. So that's it. Now we should know that in both positive and a negative gate operation, the gate current is negligible. Okay, because the gate is insulated. You should take note of that. Okay, because of the insulation here, the gate current is actually negligible because of the insulation. So we focus on what is flowing from source to drain. Okay. So we also look at the negative gate operation. If you like, it's the reverse of the positive gate operation. Okay, which is something you should be able to picture that one or explain it. Okay, all right. So more negative the gate voltage, the greater the depletion on electrons in the n channel. Okay, so the same concept, but this time around negative. What do? We put negative potential on the gate. All right, but already, what is your substrate? Okay, you should know exactly what your substrate is. This is if we take the same P substrate, okay, then it simply means that we are still having n channel. Okay, so by putting negative on the gate, what do? Okay, all right, so I've described that here. So try to just understand what's happening there. The same concept of capacitor build up here. Okay, so you see the charge separations. All right, so that should tell you something. So depletion mode, this is depletion mode n channel MOSFET with negative gate operation. If you go back, depletion mode n channel MOSFET with positive gate operation. So emphasis is on the gate operation, and we are dealing with n channel, not P channel, but n channel. Okay. We can look at some symbols here. So depletion mode MOSFET symbols. Okay. So this is n channel. What makes it so? Look at this arrow. Okay. This is source. This is drain. Okay. This is gate. Like this, we want to appreciate that there's some form of insulation. Okay. So the arrow should give you an information about N channel. All right, how is it? We are bringing more electrons towards the silicon dioxide layer, okay, or into the channel, right? So that's it. And then this is P channel, pushing away, pushing away, pushing away, arrow. The same thing goes, okay? So the B here is seen as the base, okay? What you can also see or call as a substrate. So this is source, drain, gate, base, substrate, if you like. Okay, so the characteristics of MOSFETs quickly. So the figure here is going to help us. All right, it's basically drain characteristics, okay, of N channel. We are dealing with N channel. MOSFETs. So we have ID, drain current, VDS, drain source voltage, and then VGS, that is gate source voltage. Okay, so that's that. Okay, then the characteristics of P channel are similar to this figure. The only thing is that signs are reversed for current and then voltage, so please take note. All right, now it is 9.6 is a transconductor curve, okay, so that we can talk about what we call transconductor curve of depletion mode MOSFETs, which shows the variation of what drain current with gate source voltage. Okay, so you have a gate source voltage, okay, at a certain value here. This one, everything is off entirely. Okay, so by the time we come here, gate source voltage going to put us in the off state. So this is gate source voltage, okay, is IDSS, was the drain current as far as the source is concerned. And we want to do a little bit of explanation of this curve, but before then, remember this is VGS at instance 4, 3, and then 2 and 1 accordingly. But VGS at 4 is greater than 3, greater than 2, greater than 1, in that order. Okay, so you can see these are the VGS's, if you like, and this is ID, okay, the drain current. So if I have my pen, I can say that this is ID, okay, so that's ID. Okay, so we can look at some few things. Yeah, I think what I can do, okay, maybe to help you appreciate this is when we are looking at the switching characteristics, okay, you would understand what is happening. So as far as this whole thing is concerned, this is gate source voltage at a certain value, we call it 1, which is by far a low value. Okay, at 2 is higher than 1 or bigger than 1. Okay, so that what will be the current? Okay, so when you trace this thing back to this as is, current is somewhere here, the drain current will be here. Okay, likewise this one. So you come here, okay, and then here, and also accurate, and then when you come here to, you get this. Okay, so all these points you'll be measuring current, because this is the drain current as is. You'll be measuring current. Okay, very good. So here too, you will measure some form of current. Okay, measure some form of current. So these are all drain currents. Okay, what it means is that if you put in or increase the gate source voltage, okay, you will allow for more current to flow from source to drain. Okay, so that's what is happening. as far as this curve is concerned, I'll try to explain more, get into the switching characteristics. Okay, so let's also look at the enhancement type. So this is the MOSFET. So figure 10 will help us. A and then B. Okay, so figure 10A shows its construction. So this is a construction. Okay, so you have your gate, your drain, your source, your substrates. Okay, and then this is the oxide layer. Okay, so layers of the semiconductor material NPN. Okay, so the V shows the connection. Okay, sorry, a moment please. Sorry about that break. So back, and you're looking at the E-type MOSFET. Okay, all right. So the P substrates extend to the oxide layer, as you can see. Okay, so we are looking at the construction, as you can see. There's no N channel between the D and then the source. Okay, the drain and then the source. All right. Now, when gate source voltage is 0, the VDD, okay, tries to push free electrons from source to drain, but ID, or the drain current, will almost be 0 since the P substrate has negligible free electrons. Okay, hope you are following. Okay, so when VGS is greater than 0, that's the gate source voltage. If it's greater than 0, okay, the gate attracts free electrons into the P region, okay, or the P substrates, which then combines with holes near the oxide layer. Okay, so if you begin to increase the gate source voltage, all right, you are going to attract a lot of electrons, free electrons of course, okay, into the p substrates. Okay, so this is your substrate. All right, which we then want to combine with the holes near the layer. Okay, so we want to combine with it. We are bringing in electrons. We want to combine because all displace holes. Okay, now when VGS is large enough, okay, so we keep increasing. So in this case, we are just making use of the connections. This is VGS. We increase this, okay, and then we are bringing in electrons into, this is the layer level, so we are bringing in electrons. At certain instance they will recombine, okay, but we keep increasing this, something will happen. Okay, so when VGS is large enough, the gate attracts free electrons into the p substrate region. Eventually all holes near the other layer recombines and electrons start to flow from S to D. Okay, now so this is what happens. You put let me just maybe do this to say that I am increasing. So I take a pen and then I do this. So if we increase the voltage or enough, what will happen is that previously the recombined states, because we brought in some electrons. Now by increasing this, you pull a lot or you bring more of electrons again, and by so doing you open up a channel. So it begins to open up, withdrawing, open up, so it will begin to behave as if it was the D MOSFET. So it will establish a channel. Okay, so that one, what will happen is that it will cause electrons to begin to move from source to drain. Okay, so source to drain. I'm trying to draw some arrow. So that is what is going to happen. Okay, so when the holes near the silicon layer recombines and electrons start to flow from source to drain. Now, in a hypothetical n channel, which we termed n-type inversion layer, okay, the line here is then created, allowing free electrons to flow from source to drain. Okay, so by these increments in terms of the voltage, okay, you cause electrons to come here after the recombination, and further increment, you hypothetically establish a channel and electrons begin to move from source to drain. Okay, so that is what is happening. And the minimum value of VGS, which can create inversion layer, is called gate threshold voltage. Okay, so there's certain minimum value of the gate source voltage we can create the inversion layer. Okay, and that is what we are calling the gate source voltage threshold. Okay, now okay, so this is just a repeated statement from the previous slide. So when gate source voltage is lesser than this threshold value, the transistor is off and on when gate source voltage is greater than the threshold. Okay, so that is what we also need to take care of. I think I need a pen. I need a pen. This one. Don't forget, please. Very good. So VGS greater than the threshold value, the device conducts. Okay. The MOSFET is a transistor. Okay, so that's why we are saying the transistor is on and then it's off when VGS is lesser than the VGS threshold. Okay, all right, so that's it. So E-type MOSFET conduction capability depends on the action of what? The N-type inversion layer. So for it to conduct, then how the N-type inversion layer is created with respect to the gate source voltage increment. Okay, now the figure 10.1 shows the symbol, okay, of the E-MOSFET. So that one too, you can look at it quickly and easily remember. Okay, so this is N channel E-MOSFET and this is P. Okay, so look at the arrow. But this one, look at it carefully. When you compare it to the D-MOSFET, there should be a difference. Okay, so you see this one, how we draw the gate here, the D-MOSFET is not like that. So you look at it and then you are able to tell the difference. Okay, so that's the symbol. So let's look at the characteristics. Alright, so figure 10.2, this one is going to help us appreciate the characteristics. Okay, so you realize that this curve is basically this one that I've marked here. The same thing. Okay, but there is a bit of explanation we can do here. Now, the curve depicts the variation, that is the drain current width, drain source voltage VDS for different values of VGS. So the VGS is the gate source voltage. So curve of ID versus VDS at varying gate source voltage. Just like you have the characteristic curve of a transistor that maybe we configured in common emitter mode. We are looking for the output curve. So what then do we say? We are just trying to draw a curve of collector current, okay, versus VCE, collector emitter voltage. That's why I say that that thing is it's a function of, oh come on, 1 2 so I said that it is a function of what? IC, okay, IC versus VCE, okay, VCE. So that is the output characteristic curve of okay, some eraser here. This IC can be a better one. So my IC here, let me take it like that. So we are plotting the curve of collector current versus collector emitter voltage, okay, and this one for what we call it, transistor, okay, we are taking base current to be constant. So you have at constant constant, okay, IB, at constant IB. Sorry, this is not a beta. Okay, let me get an eraser. So basically that is what we are looking at. So this is IB. Okay, I think this is better. So at constant basic area. So and this is VI. Okay, VI or IV characteristics of NPN. Like we've looked at previously, NPN transistor configured at common emitter. Okay, so this one also, as we have here, as we have here, it is nothing but drain current versus VDS at certain values of VGS. Okay, so that one too, you can just say that you can just say that, maybe if I go back to my this thing, I can equally say that my characteristic for what we call it, the MOSFET, is nothing but it's a function of what? Take this function of okay, function of, let me just have my ID, which is the drain current, okay, of VGS, okay, at a constant VGS, of course, at a constant VGS. So yes, so we'll have to look at the, so at the constant VGS. Okay, this is GS. So I get a new user here. Maybe this one will look like it. So I'll pick this one off. So this is, so at a constant VGS. This one is VGS. Okay, so that is what it is that we are looking at right now. So this is some nice S. Okay, so that is what is happening. So it's a function. So that's a function. Let's take it. That's our function. So function of what? Drain current. Okay, and VDS at a constant distance. All right. So just like we are saying that for, so this is for E MOSFET, if you like, E MOSFET. So you can consider this, and then I think the other one also we were looking at, which I put on the screen anyway. So I can yeah, so I was saying that, okay, for your BJT, so for your BJT, you basically have the characteristics to be F of IC, okay, versus VCE, okay, at constant, so let me just shorten it, at constant IB, okay. So this is for a typical MPN, okay, MPN, common emitter configured transistor, okay. So the output characteristics will be this. So this is the output characteristics. Okay, so take note of this. And this one is the drain characteristics, okay, drain characteristics, which is basically the output characteristics. Also looking at the drain source, okay. So this is the drain source, and then we are making use of the gates, okay. So gate operations, so gate source. I told you that the gates and then the substrates, gates and then substrates, straight, okay, and so on, whatever. They are the same potential, same potential, so you don't forget to. All right, so let's go back. Yeah, so the curve depicts the variation of these for different values of this, okay. So that's what we have. So when VGS is less than this, ID is almost 0, okay. So that's what you can see here. VGS, anytime VGS is less than certain value, and let's say this value here is bigger, so if it's less than that, your drain current is almost 0. So anything that is happening here, okay, anything that is happening here, let me go back. Anything that is happening here is basically around 0, okay. So you see 0, 0, 0, 0. This is a line. This is X axis or VDS axis. So the thing is almost 0. The device is on when the VDS is greater than the VDS threshold. So anytime it goes beyond the VDS threshold, then you can start reading some current at the drain side and see it's on. That's what we mean. So this also shows the transconductance so the transconductance curve, all right. So that so it starts from VGS threshold, because when VGS is less than VGS threshold, the device is off, okay, and ID is also 0. So ID is given by this expression, okay. So we can derive an expression to tell the state of the drain current, which is this, okay, VGS minus VGS threshold, and is equal to VGS as a state where VGS is on minus VGS threshold times the drain current at which the whole thing is actually on, and we can get the true state of the drain current. So we should note that MOSFET has a very thin SiO2 layer, or thin silicon dioxide layer, you see, which is always kept thin to ensure the gate has good control. I think I should underline that one, or the student will have to underline. I emphasize it, you underline. So it has a good control over the gate's current, okay. So keep it thin. In fact, not just thin, very thin, okay, so that your gate can actually have control over the current, the gate current, okay. So that is what is happening. So the thin layer is destroyed if a voltage higher voltage than the rated value is applied. So make sure you don't apply higher voltage than the rated value, okay. So that's what is happening. All right. So let's look at the switching characteristics. your power MOSFET, in fact, for us here, we are just, not that we are just, but it's a switching device, if you like. So we want to make use of it as such. Okay. Right. So the figure here is going to help us. Figure 11.1. Okay. Now, the turn-on characteristics of power MOSFET is what we have here. All right, and you have to be very careful. Figure 11.1 is including this figure, which is VGS versus time, and then ID, drain current versus time. So all this whole stuff, let me do it like this so that you would understand what I'm saying. All this stuff, all this makes for the turn-on characteristics curve. So you don't just go and draw this one and then you say, oh, you have turned on the thing. You don't just go and draw this one and say you have turned on the thing, or draw this one. No, they work together. Okay, so take note, please. Now, as VGS increases, as the gate source voltage increases, drain current remains 0 till T is equal to 1. So see, this is your gate source voltage. Okay, and this is a threshold value. Okay, it is increasing. Okay, so at certain points, that's time T1, will record some amount of voltage, which we are saying it is threshold. It is threshold because at that point, when we trace it, let me try and do that. I think and is not so fast like I'm saying the So you see, so something like that. You understand? Now, at this point here, here, current starts conducting. It only start conduction when the voltage gets to that threshold value. Okay, so that's why we are calling it time T1. The thing will start conducting. Okay, all right. So at T is equal to 1, VGS is equal to VGS threshold. It means that the gate source voltage at this point they are equal. Okay, and MOSFET start conducting. Okay, so note ID is a function of gate source voltage and gate source threshold. So you should note that one. All right. So gate source voltage has to be increased to a value well above. Okay, so well above VGS threshold for drain current ID to rise to its full value for the MOSFET to fully conduct. Okay, so well above. So that is what we are looking at. So it will get to a certain value and the thing will conduct, and the drain current will now become a steady state current. So like this, there's a drain current, it's conducting. But it's conducting when we have reached a certain value of the gate source voltage around here. Okay, so that's what I mean. Now, so the time T, which is equal to T1 plus T2, is then the turn on time. So you can see, where is turn on? This is turn on. This whole thing, that is the time. So it's T and then T2. Okay, so 0 to T one time, then from this T to another T2 another time. You sum all these, you get T on. So, and at T on, ID has reached its full value, and the MOSFET is fully conducting. That's it. So let's look at the turn-off characteristics. Okay, switching characteristics includes turn on and then turn off. Please, figure 11.2 is that which is describing the process. If you like, the turn off is just the opposite of what the turn on. What do? Reduce your VGS. Okay, at the time where you've reached the peak, from that time, reduce the VGS. It will decrease the drain current. At certain point in time, the thing will go off. Okay, so that is what it is here. That's what it is. Okay, so maybe basically you can just look at it. So during the initial time, VGS decreases from its initial value to a value more than VGS threshold. At this time, ID remains constant, as you can see in this figure. This is the drain current. I told you the thing must work hand in hand, voltage and then current. So that's it. See, all this place, the thing is still steady. Then, when you get to this place, the voltage is now coming down. And even that, you still have not reached the threshold. So you still have some current conducting. It is only when you get to the threshold value. So anytime VGS, I think, anytime VGS so that if we have if you have VGS lesser than VGS, okay, threshold, the device will go off. Okay, your ID will become very drain current will become very small. Okay, very small, such that MOSFETs will turn off. Good. So that is what is happening. Now, so that is the case here. Okay, so basically that's the explanation I can give here. So MOSFET is very fast electronic switch. Okay. Okay, so maybe before 10, the turn off can be accelerated by making VGS negative. So if your gate source voltage make it negative, you speed up the turn off process. MOSFET has a lower switching time than other BJT. So the question is, lower switching time than other BJT, is this an advantage or disadvantage? Okay, you should understand that the underlying factor is lower switching time. MOSFET is very fast electronic switch used in both analog and digital devices. Okay, used in amplifier circuits for low power audio and video amplification. Okay, it's also used in SMPS. Okay, I guess you can decode it. SMPS, that's switch mode power supply. Okay, all right. Now I want to talk about IGBTs, insulated gate bipolar junction transistor. In fact, I didn't bring in the junction here, but in some literature, some books, you will see IGBT. Okay, if it is omitted, doesn't mean it is not there. Okay, all right. So let's introduce ourselves to this one. So this is another form of power electronic switching devices, and this one is a very correct one. So we'll look at what it is. Okay, that's not to say the others are not correct. Don't take me for the wrong side. Okay, so BJT has lower power loss but long switching time, mostly for 10 off, okay, or at 10 if you like off. Let me see if I can get a pen. So BJT has what? Low power loss. Do you see that advantage as an advantage or disadvantage? But long switching time, do you see this one as advantage or disadvantage? So decide for yourself. Then MOSFET, on the other hand, has very fast switching characteristics. So very fast switching characteristics, what do you mean by that? Okay, that's a good question. Low turn on, okay, and turn off. So you should know what that means. That is the explanation of the very fast switching, but has or have high power loss. So is this an advantage or disadvantage? Okay, so from these two points, okay, or preambles, we can do something. IGBT combines, so the underlying element is that it combines the advantage of BJT and MOSFET. Okay, that is to say that the low switching time and low power losses. So it is taking this one from where? If you tell me. And then it is also taking this one from where? From BJT or MOSFET. So IGBT is making use of the advantages that we have in this and then in this, and then throwing away the disadvantages. In this case, we will get a better device, a super device that supersedes BJT and MOSFETs far. Okay, very good. IGBT is a 3-terminal power semiconductor switch used in controlling electrical energy. Okay, so you see, 3-terminal. It was introduced in the early 1980s. Okay, that is if you want to go into some histories. A lot of you guys were not born then. Only some of the old guys. So figure 10, okay, is quite similar to what we call a VDMOS. Okay, so you have what we call a vertical, or you go and find a VDMOS. Of course, you know what MOS is anyway. So, but with P plus layer, that is the injecting layer, to form the drain. So the M plus layer, which is the buffer layer, establishes junction J2 with the injection layer. Okay, so this point is just giving us an idea about what it is that we are going to look at here. point options. Okay. So yeah, so basically this is the configuration of an IGBT. Okay, so that you have how many layers? 1, 2, 3. Okay, 4, and then 5. But we will not accept 5 layers because this is n plus, this is n minus. They are all n, but just a variation in terms of the density. So 1, 2, 3, and then what? 4. So this is a 4-layer device, but 3 terminals. So please take notes. So you see, you have your source, you have your drain, you have your gates. Okay, all right. Now junction J2 and J3. Okay, maybe before then, I have an N plus layer which establishes J1. Okay, with the injecting layer. So where is the injecting layer? This layer. Okay, now this layer forms a junction with another layer, the M plus layer. This M plus layer, we call it the buffer layer. This is it, and it makes a junction J1 with the P layer. Okay, and the P layer here is the injecting layer. Okay, so that's it. J2 and J3 are also present, hence parasitic thyristor. Okay, you know what the parasite is? Some of you can be parasites. Only consuming. Anyway, so you will form an SCR, okay, that's a thyristor, which is present in the device. Okay, in this SCR, you have not intentionally created it. By constructing the device or configuring it, it shows up. Okay, so when you go back to this, we're talking about this junction J2, then J3. Okay, so you have this layer and then this layer. Because of that, you can form a junction here. You have this layer and then this layer, M plus layer, M plus layer. Because of that, you can form this. So what do we have? We have 3 junctions. So your superconductor device that you now have 3 junctions ceases to be ordinary, what do we call it, diode transistor based device, but now we can call it a thyristor. Thyristor has 3 junctions. Okay, all right. So I have an assignment on this, especially the parasitic thyristor. What is going to help it go off or prevent it from coming on? Okay, so I'll give you some assignment on that. All right. Okay, so that is what is happening. So the body region is made to prevent the undesirable turn on of the parasitic SCR. Okay, so my assignment is going to be based on that. Okay, so the junction J2 is blocking junction. Okay, so where is the blocking junction? So you have J2, okay, so J2, right, so that's so you have your J2, which is the blocking junction, and then M plus drift region holds the depletion layer of blocking junction. Okay, so your M plus drift region. Okay, we have the drift region. Drift region. Now, if you also look at this, remember we said or we mentioned something about volatile drift region with every one of the PN devices. That's if you remember. Okay, so without M plus, okay, buffer layer, IGBT has large reverse blocking capability. Okay, so if this M plus buffer layer is not there, okay, the IGBT has a very large reverse blocking capability that it can deal with reverse voltage, okay, in a very high magnitude. So we call that kind of device symmetric IGBT. Okay, that is where your N plus buffer layer, okay, is absent. With M plus buffer layer, okay, being present, IGBT junction J1 has small breakdown voltage, and thus IGBT has little reverse blocking capability, anti-symmetric. Okay, IGBT is the name. Alright, so buffer layer speeds up device turn off. Okay, so you need a buffer layer to speed up it turn off. Now some IGBT do not have N plus layer as we have in the figure. So if M plus buffer layer is absent, we can call it non-punch-through IGBT, NPT IGBT. Okay, if it is present, we call it punch-through PT IGBT. Okay, if the layer is present. Okay, so that's for information. Now, characteristic curve. Okay. So the VI or the IV characteristics of this IGBT. Okay, so we see drain characteristics of the IGBT. Okay. All right. So the figure is helping us. Okay. Now VRM is a reverse blocking voltage. So that is this one VRM. Okay. So apart from that, it's the same concept that we saw earlier on, that this whole thing maybe I can just see that this is nothing but a function of ID, comma, VDS, okay, at constant VGS. Okay. All right. So we have what we also call BVDSS. Okay, which I'll explain quickly. All right. So basically, that is the characteristic curve. So it's nothing different from what we are we just look at MOSFET. Okay, remember IGBT is nothing but or let me say this is coming from BGT, JT, and MOSFET. So that is to say that IGBT in totality is a fraction of what? BGT and then MOSFET. We put those two together to form our IGBT. Okay, so that is okay. And then we can maybe talk about some two things. J1 blocks reverse voltage, okay, like we seen earlier, junction J1. An IGBT without the N plus buffer layer has a higher reverse blocking capability. So that's I think I talked about it already. An IGBT required for blocking high reverse voltage does not have N plus buffer layer, and I hope you know that. So junction J2 blocks forward voltage when IGBT is off. Okay, so it has to do so, and we talk about undesirable turn on of the parasitic thyristor. We must take care of that. So J2 plays a role. So BVDSS is the breakdown voltage, okay, in the forward direction. So that's this BVDSS, okay. All right. We can also talk about transparency curve, okay. So that when VGS is less than VGS threshold, the device is in off state. Okay, you see this statement again. The curve is almost linear except when drain current is very low. So the symbol here is what we have here. Okay, so this is the symbol, and take note of this. Take note of this. So when we say collector, then you should take your mind back to BJT, isn't it? BJT. You can easily say collector in bipolar junction transistor. You can easily say emitter in bipolar junction transistor. Okay, gate. So for our discussion here, as far as BJT is concerned, collector is the same as drain, emitter is the same as source. Okay. Then if you like, our gates can be seen as the base. So this is a parasitic thyristor and the latch up in the IGBT. I really don't want us to spend so much time on this, okay, so we can just look at the switching characteristics, okay, but I will teach you thyristor and then you can come back to look at these things, which is a simple thing anyway. Complete IGBT equivalent circuit. Okay, this whole thing is very simple, but we have a lot of things to do anyway. Okay, you see, this whole thing is a MOSFET, a particular type of MOSFET, if you remember. I've shown you MOSFET. You see, this is an NPN transistor. Okay. So you see a MOSFET and then a BJT. Okay, so the equivalent circuit we can easily quickly pull it out, and then this is a PNP. Okay, so this is an equivalent circuit, right? So you can look at it later. I need to move fast. I have so much to do. Okay, so let's look at the characteristics of the IGBT. That's turn on, and then also look at the turn off. So figure 10.4 helps us to look at that. So 4 distinct time intervals. Okay, TD on, TRI, TF1, TF2. Okay, 1, 2, 3, 4. All right. So during TD on, the gate current charges. Okay, so you see, we're talking about charges the input capacitance at a constant rate till the gate source has the emitter voltage VGS, which is VGS threshold. Okay, so these are VGS. We charge it, so we get to VGS threshold. Okay, what is that way? So like I also told you earlier, switching characteristics involves both gate source voltage and then drain current in one curve. So please take notes. Take notes. Okay, so during as that happens from VGS to VGS threshold, okay, look at where the current is. The current is actually 0. So when you get to threshold value, before it will start conducting until we exceed certain value of the threshold, we cannot rise to a steady state value of the drain current. So that is what is happening here, please. During interval TRI, the load current is diverted into the device and increases to its steady state value, that is I on. Okay, so there's a steady state value, current is on. Okay, steady. All right. So at this point, the thing is conducting. The only thing you can do to it is to cause it to go off. Okay, by decreasing the gate source voltage. That's all. So the voltage VDS remains almost constant till the end of the time. So the drain source voltage, okay, will virtually be constant. This is what we are talking about. Drain source voltage VDS for on, it basically remains constant. All right. And then during TF1, okay, it decreases rapidly and VDS declines slowly till it gets to the steady state value of VDS on. Okay, so like you can see here, till we have here that kind of thing. And IGBT, drain is same as collector and so on and so forth. Okay, so I talk about those things. So the switching off, okay, or the turn off. So we can look at this one also. So figure 10.5, that's turn off characteristics. Okay, so basically, if you like, it's just the reverse of what the turn on. Okay, so the same concept. All right. So the turn on, the turn off is achieved by decreasing the VGS. Okay, and is the same as VGE. Okay, so that VGE is nothing but what? The gate emitter voltage. Is the same as the gate source voltage. So from its initial value of VGS threshold. Okay, so the time interval of VGS to decrease from its initial value to VGS threshold is the time TD off. Okay, so TD off. So during this time, ID and VDS remains almost constant. Okay, so for the TD off period, okay, you can see where is our ID? There's this one. It's remain constant until we cross the threshold value coming down. Okay, then the thing will start decreasing. And then it will come to 0. So that is what is happening. As it happens to VDS, it's going to be steady. So the decrease of ID occurs in 2 intervals. Okay. So during this, okay, ID decreases rapidly whilst it decreases slowly during this, okay, till it becomes 0 as we have in the figure. Okay, so it's just a matter of causing a decrease in the gate source voltage till it goes way below the threshold value, then the whole thing starts decreasing. Okay, so basically this is the gen of characteristics. Okay, all right. Applications. So this are some of the things we can say about this kind of stuff. Applications. Okay, so if in AC and DC motor drives, okay, unregulated power supply, that's UPS systems, okay, to combine the simple gate drive characteristics of MOSFET with a high current and so on and so forth, switch mode power supplies and so on and so forth. So these are some applications. You can read and you can even research on more applications of IGBTs and so on, the detailed ones. Okay, so a lot more here. Okay, so for now, let's say that for the session of our PN junction devices, considering diode, signal, and then power, and that of BJT, both traditional for ordinary or signal, and then a power BJT, likewise MOSFETs, okay, and these IGBTs that we have looked at right now, we realize that they are all switching devices. You can use them for switching, and they have certain common characteristics because of the PN junction concepts, and they are very useful in several number of applications. Okay, so you can read more material to give more information. Don't limit yourself to this slide. I gave you some references, make use of them. There are some hard copies that you also need to arrange and pick a copy for your further reference or study. Okay, all right, so it has been a nice time coming to you this way again. So until then, keep studying, keep researching, keep updating yourself, and sooner or later you'll be taking your tests, your exams. So please never stop learning. Thank you. Bye bye.